gentlemen, today's class recording has started. And I'm moving the microphone so it probably sounds like really loud and stuff, but all right. So yesterday, we introduced the beginning of atomic theory. So the fact that we call it atomic theory should tell you two things, right? What can we deduce about atomic theory because its name is atomic theory?
Has to do with atoms.
Has to do with atoms.
It's
trying to explain things, right? It's trying to explain the existence of atoms. And so at the beginning of class yesterday, we talked about the two original ideas of where does matter come from or what does matter consist of. So we talked about Aristotle, and then we talked about Democritus. And we talked about Aristotle's idea that everything in the universe is composed of the same materials, the same four materials that just happen to be joined together in different recipes, right? In a different combination to produce something that is different from something else. Like we talked about the rock and the wood block from yesterday. And then Democritus said that everything is composed of its own material. So this rock's material is different than this wood block's material, but that this rock is really just a big collection of very, 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 very small pieces of rock that just come together to form this big rock. And this wood block is a combination of very, 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 very small pieces of this wood block that just come together to form a big wood block. So we said that these are both theories because they explain things, but they lacked experimental evidence. They lacked data to support one versus the other. So that remained the case until we got to the scientific revolution, the Renaissance, the Enlightenment, whatever you want to call that period of time, right? So we're looking at three scientific laws that scientists, through measurements, have come to the conclusion, right? Laws tell us what's happening, but not why it's happening. So we knew that mass was conserved. We knew that substances had a constant composition, right? Like the water was 2 parts hydrogen and 1 part oxygen, and it was always 2 parts hydrogen and 1 part oxygen. But we also knew that hydrogen and oxygen could come together to form multiple compounds, like water and hydrogen peroxide that we talked about yesterday at the end of class. So these are laws. This is what's happening, but then once you figure out what's happening, we try to explain it. And that led us to our first atomic theory based on experimental evidence, and that was put forth by John Dalton in the early 1800s. Okay? So what Dalton was saying was, okay, if I know these things are true, these laws, which that's why they're laws, right? It tells us what is happening. If these things are true, it has to be because of the fact that we have these things called atoms, right? And so Dalton said some things that was trying to explain the observations, right? He said, all right, if mass is conserved, then that means that atoms are indestructible, that we can't break them apart. We can't divide them. They have to remain the same beginning and end, right? He's trying to explain these observations, okay? So Dalton's atomic theory is our first theory based on evidence that atoms actually exist. Okay? Good with that. All right. Theories are good until when? So there's new evidence, or Primo, what were you going to say? Disproven is kind of a harsh term, right? Because do we actually prove anything? No. We look for patterns, right? And theories explain what's happening. So a theory is good until it can't do what? Until it can't explain what we're seeing. Then we have to somehow modify that theory. Okay? Good? All right. So we're going to skip over this part about Becquerel and Marie Curie. We'll talk about that when we get to nuclear chemistry and stuff like that. But I want to pick it up here. And you don't have these pictures, but this is a picture of something called a Crookes tube or a cathode ray tube. And Crook is a guy, he's not a criminal. Okay? So I'm going to explain it here real quick, and then I'll show you a short but so awesome video to explain it a little bit more. Okay? So, top right here is a picture of a Crookes tube. A Crookes tube is basically a glass tube, kind of like these lights that go in these fixtures in this room. Okay? It's a glass tube, and they have taken most of the air out of it. So it's a vacuum inside of it. Okay? But what scientists realized was if we ran electricity through this tube, so hooked up the two sides of it to a battery, it would glow and it would produce this like green light that looked a lot like a laser beam. Why? How? No idea. Just knew that it happened. Okay? But what we started realizing was, as we looked at observations and made more measurements, that this green light wasn't really light at all. Okay? So I'm going to show you this awesome video, and then we'll talk a little bit more. So just a little precursor. This video is 1 minute and 9 seconds long, but it's super awesome. Okay? So I hope you can tell that I'm being sarcastic when I'm describing this video. Okay? So first, I'm gonna pause the class recording when I play the video, because if it records something streaming, it just makes the video file like really, really long. But anyway, so here's this dude who's the video in his suit and his goggles, because you got to make sure your eyes are protected. Okay? Just an FYI, like when I was in school, this is what science movies looked like. Like some guy standing in a laboratory in front of the periodic table with goggles on. Okay? So, all right. So again, let's watch this short little video, and then we'll discuss it in more detail here in about 1 minute and 9 seconds. Here we go. All right, recording's back on, everybody. Okay, so in the video, we saw this. This is the cathode ray tube. So when he flips on the switch, right, electricity flows from this end of the tube to this end of the tube, and we see this green, what appears to be like a laser beam, show up in the middle of the tube. But as you saw a little bit later on, when the magnet came close, right? Oh, it says actually like, come on. Okay. So here, when we bring the magnet close, it looks like the laser beam is actually bending away from the magnet. Okay? And when you flip the magnet around, it bends the other way. So, scientists start realizing that this is telling us something about this green laser beam. First, is it a laser beam? No. If it was a laser beam, the magnet wouldn't do anything to it. Light is just light. It's energy. It doesn't have magnetic properties. The light wouldn't do anything if it was just, the laser beam wouldn't do anything if it was just light. So we start asking questions and looking for answers to those questions. And then in 1897, a very famous experiment called the cathode ray tube experiment was conducted by J.J. Thomson. Okay? I think is John Joseph, but I'm not really sure on that. Okay? So here is a picture that looks similar to what the experiment, or what the demonstration that you saw in the little video. In this picture, the green line represents the laser beam. Sorry, here it's a black line. This black line that goes across the screen represents the laser beam. And you can see here that there is a positive charge magnet and a negative charge magnet on either side of the tube, and the beam bends towards the positive side. Right? What does that suggest about the beam itself? If it bends towards something that is positive, what should that tell you about it?
It's negative.
It's negative, or it's made up of something that is negative, right? So, what J.J. Thomson realizes is that this beam of light is not a beam of light. It's actually a bunch of small, negatively charged particles. And he calls those particles, eventually we call them electrons. So, Roman numeral number 4, J.J. Thomson and the cathode ray tube experiment. The cathode ray tube experiment is responsible for the discovery of electrons. Okay? He discovers that these electrons exist because that beam bends towards a positively charged. So that means that that beam itself must be negatively charged or made up of negatively charged things. Dalton's atomic theory said that atoms were the smallest thing out there and that they were indestructible. But what happens here is that Thomson finds evidence that there is actually something that is smaller than an atom. So Dalton's theory explained stuff until it couldn't explain things anymore. So if a theory can't explain our observations, now we have to come up with a new theory or a new picture of what's happening. All right? So J.J. Thomson does the cathode ray tube experiment. Oh, 1897, by the way, for the cathode ray tube experiment. So if you want to jot that down, maybe in the margin or something like that. So Dalton was the early 1800s. Cathode ray tube experiment was the late 1800s, or 1890s-ish. Okay? So once Thomson discovers that there are these negatively charged electrons, he comes up with his own theory or his own model, which we call the plum pudding model, or he called it the plum pudding model. First, I don't expect that any of you have ever had plum pudding before. That doesn't sound very good at all, does it? No. So, instead of thinking of this as plum pudding, because most of you probably don't know what plum pudding is, let's think of this as a chocolate chip cookie, because I think most of you have had a chocolate chip cookie before. Okay? I would imagine. If you haven't had a chocolate chip cookie, you should. They're good. So. All right. Here, sorry, right-hand side. What he's saying is that no longer is the atom the smallest thing out there. There are smaller pieces out there which we call electrons. And those are represented by these blue dots within the atom itself. The blue dots are negatively charged. If there's a negatively charged thing, what else should there probably be? A positively charged thing. So what Thomson is saying is that if this is sort of like representing, or if this is like a chocolate chip cookie, the chocolate chips themselves are the negatively charged particles, the individual negatively charged pieces. But the cookie part represents all the positive stuff that goes along with the negatively charged electrons. Okay? Good? The other way you kind of think about it, you ever have Jell-O where somebody has cooked the Jell-O so that there's little pieces of fruit actually embedded within the Jell-O?
Yeah.
Kind of sort of the same thing, where the little individual pieces of pineapple are the electrons themselves, but the lime Jell-O that surrounds that pineapple would be like the positively charged stuff, or whatever flavors you make that salad out of. Okay. Good? All right. Thomson discovers the negatively charged electron. What do you think people start looking for after that? The positive charge that goes along with that negative charge. Okay? So, Dalton brings us the first atomic theory. J.J. Thomson discovers the electron. The next guy you need to know about is Rutherford. Okay? So first, you also need to know that Rutherford didn't actually do this experiment. His students did it, but he gives credit for it because they were working for him. Alright? Kind of so when they wrote the lab report that summarized this experiment, Rutherford did none of the work but got to put his name first on the paper. So, good for Rutherford. So. Alright. Go ahead and write this down, and then I'll show you some things that represent this, hopefully more clearly. Okay? So go ahead and write these things down, and then I will show you a simulation that hopefully represents this one. So Rutherford students conduct an experiment that today we call the gold foil experiment. So they took a sheet of gold foil, kind of like the aluminum foil that you have in your kitchen, okay, or that we used in lab the other day, but made out of gold. So just a thin sheet of gold, okay? So I'm going to get out of here, and I'm going to take you to this website right here. Okay. Over on the left-hand side, this is a representation of what happened. So you'll see this big blue dot right here. There's a machine, and underneath it says alpha particles. Okay? We know today that alpha particles are a type of radiation. Okay? Scientists at the time had no idea what alpha particles were, but they did know that they were positively charged. Okay? So keep that in mind. Alpha particles, they don't know what they are, but they know that they have a positive charge. Okay? So here's how the experiment goes. Let's say this rock is radioactive. It's not. Let's say that it is, though. Okay? And part of its radioactivity means, or its radiation, is that it gives off alpha particles. So for the most part, you want to keep that rock in a secured box because you don't want that radiation to get out. Okay? But if you poke a small hole in the box that your radioactive rock is in, you've now created, in essence, a gun that fires alpha particles. Okay? Does that make sense? Right? Little hole in the box, alpha particles come out, and you've got a nice little stream, like a squirt gun of alpha particles that get out. Okay? Rutherford students took those alpha particles and shot them at a very thin, small piece of gold foil. So just like aluminum foil, but made out of gold. Okay? So I'm going to turn on the gun and we'll see what happens. Okay? Here we go. So the purple represents the alpha particles that are being shot at the piece of gold. This big square in the middle is kind of like looking down from the top on the piece of gold. The alpha particles are coming from the bottom of the screen, and they're encountering the gold foil at this point in the simulation. Okay? What are you seeing about most of the purple alpha particles as they encounter the gold foil? A lot of those purple lines are pretty straight, right? But what's happening to some of them? Yeah, they're kind of like getting deflected somewhere the other way. And if you look at some of them, you'll see that some of them even like bounce right off of it. Okay? Bounce right off of these yellow dots. Okay? All right. Knowing that the alpha particles have a positive charge, what can you tell me about the yellow dots? Good. They are also positively charged. Drew, why do we know that?
Because they get pushed away.
Good. So, like things repel or push away other like charges. So these purples that are being pushed away from the yellows has to mean that the yellows also have a positive charge because the purples are bouncing off of them or pushing away from them. Okay? Good with that? You okay with that? All right. So, you make these observations, and these are the observations that Rutherford students made. They notice that a lot of the alpha particles that they shoot at this piece of gold foil actually go straight through the piece of gold foil. Alpha particles are super, 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 super small. Okay? They're actually parts of an atom that we know now. At the time, we had no idea what they were, but now we know that they are portions or very small pieces of an atom. So most of those alpha particles just travel in a straight line and they go straight through. So here I'm going to do this. Here I'm going to change my protons from 79 down to 20, okay? And now look what happens to almost all of the purple lines, right? What are you seeing a lot less of? Yeah, there's a lot less bouncing, there's a lot less of those things that are changing directions and stuff like that, okay? Taking protons from 79 down to 20 does what to the positive charge in the yellow dots? Less positive, right? We'll get into that a little bit more tomorrow, if that makes sense, because you can remember something critical to remember, that's fine, right? But we'll get into that a little bit more tomorrow, okay? So, if there's less positive charge, these alpha particles are less likely to bounce away from the other ones, okay? Good? You okay with that? All right, so we make observations and then we draw conclusions from those observations. That's what we do. So here's the conclusions that Rutherford students and Rutherford made based on their observations. Okay? 1. The atoms that make up that foil of gold that the alpha particles ran into are almost all empty space. Most of the gold foil actually consisted of nothing. But there is this tiny, dense part that the alpha particles would occasionally run into. And that they call that tiny, dense part the nucleus of the atom. The nucleus of the atom contains almost all of the mass of the atom. So it's very small, but it's also very dense. And it has a positive charge, because those other positively charged alpha particles would sort of jump, bounce, deflect off of them. Okay? Okay with this experiment. Understanding kind of what's going on. All right. So, like I said, this unit, there's a couple of people and a couple of experiments and a couple of dates that I want you to know, at least in chronological order. So, hold on. It's not like 10 minutes. I don't know. Let me wrap this up. So if you put your outline away, you might want to pull it back out because there's important things I want to make sure that we review. Okay? All right. So the first person you need to know is Democritus. Okay? What does Democritus do, or what is Democritus responsible for? You can look at your drawing. Say again? Jay, go ahead. Because he said, what did he say about this rock? Go ahead. It's made up of smaller pieces of rock. That this rock is just a big collection of very, very small rocks. Okay? Good with that. All right. Dalton. Dalton's atomic theory. Why is Dalton's atomic theory important? Go ahead, Chris. Okay. He says that chemical elements are made up of atoms. That's part of his theory. That's also what Democritus said, basically, right? Why is Dalton's atomic theory more accepted than Democritus's atomic theory? Good. It was based on those three laws, right? It's got some experimental evidence to back up what he's trying to say. And so that's why Dalton's atomic theory is important. Dalton's atomic theory, early 1800s. Okay? The next guy you need to know is J.J. Thomson. First, what experiment does J.J. Thomson do, or what experiment is J.J. Thomson credited with? What do we call it? The Crookes tube. So usually we call the experiment the cathode ray tube experiment. Okay? What is the gist, or what is the important conclusion of the cathode ray tube experiment? Okay, electrons, right? There is some piece of an atom that is smaller than an atom, negatively charged electron, okay? And then finally for this one, right, Rutherford and his students, what experiment do Rutherford and his students conduct? The gold foil experiment, that's what we do, right? So that's what it consisted of. We usually just call it the gold foil experiment. What's the gist, or what's the big conclusion that comes out of the gold foil experiment?
Atoms are matter, mostly space.
Mostly space, except for what?
Except for the nucleus.
Except for the nucleus. So all the positive charge that an atom contains is concentrated in the nucleus, that very small section right in the middle. Okay? All right, good. One last thing. You have like 5 minutes, so it's not like I'm rushing you. All right, keep in mind that as far as the calendar goes, over the past 2 days, a couple of things to look at. First, there's some pages in the book that review this material, so you might want to check that out to make sure that we're reinforcing the things that we're doing in class. And then tonight, there's a couple of questions that are just sort of basic recall questions about our atomic theory and the development of atomic theory and how we got to know about the atom. Okay? We are probably looking at first quiz for this section being made available to you on Thursday night. So that's probably your first quiz for this unit. Okay? Good? All right. Have a good day.